Okay, let's look at to the next example given in the page. Given on page is 308, exercise 7.5, and for this case we are given an infinite surface current which positions at plane y equal to 1, and now the surface current has 50 milliampere per meter, and now it is pointing out in positive z directions. So if you want to draw in 2D view, it means that on xy plane you are going to see the current now becoming like a dot, right? Because the current now is pointing up or in z direction. So if you draw in 2D, you will look current like a dot as shown here. So now we are going to find the H field at this point, or at this origin 0, 0, 0, and now we need to draw our Amperian loop to apply this ACL. Alright, so for the loop you are free to choose any structure or any types of loop. Either you can use circular loop, you may even use triangle loop, but the best loop to be used here, actually you just use rectangular loop, because it's much easier for us to analyze every path within the loop, right? So let's say I choose to use rectangular loop. So the first one we had the path will go from this point to any point, let's say that point, and then for the second path from that point to this point, and then for the third path from down here up to that one, and then the last path from this point to the back to the original positions. So that is going to be your fourth line. So if you want to draw the directions, you can just put the arrow as such. So that's the direction from this one to this point, this point to this point, and the next point over there, and lastly as shown there. Okay, this is our rectangular shape or loop. So let's define our first edge over here becomes your first edge, and then your second edge over here becomes your second edge, and then the third edge over here becomes your third edge, and then the last edge over there becomes your fourth edge. Alright, so based on this ACL equation, we know that these integrations will consider the whole path, isn't it? So since we have 4 different paths, so we can actually decompose these equations of integrations becomes into 4 different paths of integrations as shown down here. The first integrations for the first path 1 to 2, 1 to 2, the h dot dl number 1, and then plus the second path 2 to 3, again h dot dl number 2, and then the third path of from 3 to 4, just 3 to 4, h dot dl number 3, plus, and last from 4 to 1 back to the origin, 4 to 1, the h dot dl number 4, and lastly equal to the R enclosed. If you see closely at this particular loop, the only current that exists within this Ampere loop actually only exists from this point to this point. It means that we can simply find the total current that actually enclosed within this length as here the JS dl, because the JS actually has unit of ampere per meter. So if you want to find the total current, just times with the dl, right, the meter, the length. Okay, now let's do it one by one. Look at the first path, which is from 1 to 2. Alright, for the first path from 1 to 2, this path actually lies along the x-axis, so automatically we can just simply change this dl1 becoming in x dx. So you just care about the axis, right? Don't care about the directions yet now. And now how about the h? Now how do we know that the h at this region either in positive x or negative x, or how do we know? So we can just use the simple method using the right hand rule. If let's say, okay, let's take few example of few line current. Let's say this is my first line current, right? First line current. So if you use a right hand rule, this line current become your right hand thumb, and your other right hand fingers will represent the h directions. So from here you can simply find the h field actually within becoming like that. Alright, so your right hand thumb is here, your line current coming up. So the rest, your right hand fingers, the rest becoming your h directions. So let's take another sample current. Let's say another line current nearby. You also will have the same direction of h, which actually will go same in that directions. Agree? And if you keep doing for the next line current nearby, you also will see the same pattern, right? All the h field will go in that direction. So let's say we place this series of line current along the x-axis. So we know that at this region, okay, all the h field will go in a positive x directions, as shown here. Positive x directions. Meanwhile, for the above region over there, so the all h field will go to the opposite positive h direction. So you can simply shows the h field as such. So now the has h in negative x component, right? So in short, we can simply say that at this particular region which is less than y equal to 1, all the h field will go in positive x direction. Meanwhile, for the region over here, which is region y equal to more than 1, all the h field will go in the opposite direction, which is in negative x direction. So if I want to draw the h field, you'll see that way in positive x direction. For this side, will always have a negative x direction, right? So back to these equations. For the first one, for the first path, we know that already based on this simple analysis. We know that at these regions, the only h will appear in positive x directions. So the h over here we can simply change to becoming h in x in positive x directions. Okay, so let's look at the next part over here. So the second path from point 2 to point 3, to point 3, so this line or this path actually lies along the y-axis. So just change this dl number 2 becoming y dy. Agree? So how about the h? If you see closely from this diagram, from point 2 to point 3, we have two types of h field. For the first one, from this side, the h field actually in positive x directions, and for this side, the h field in negative h direction. So we can or simply put both direction plus minus in x directions. Alright, okay, let's proceed to the next path, the third path, which is from point 3 to point 4. Again, this path lies along the x-axis, so you can simply change this dl number 3 becoming x dx. And again, at this region, the only h field that appears actually in negative x direction, so you can simply convert this h become negative h in x directions. Okay, how about the last path? The last path actually from point 4 to point 1. Again, this path lies along the y-axis, so you can simply convert this dl becomes y dy. and then the H field that exists within these two regions, actually they have both, right? From here to here we have negative Hx, and from here to here they have positive Hx. So you can simply put positive, negative in x directions. So let's do the dot product between the H and the L. You can see from here the x dot y will have 0 product, and then again x dot y also will have 0 product, right? So what left? We only have this first and third integral path. So let's write again the equation. Okay, integration here, the Hx in x directions dot x dx, and plus, now the H, the third is negative, right? So put a negative Hx x directions x dx plus now js dl. Okay, now let's assuming that the length, alright, the length is this partial actually h. Is it okay? The length for this path actually h. So we know that from this integration path, for the first path from 1 to 2, the movement or the changes of the limit actually from 0 to the h. So you can simply put here 0 to h. And then for the third path over there, again from 3 to 4, we can see that the limit changed just from h to 0. So you can simply put here h to 0. Okay, and how about the gs? Okay, the gs actually, the I here, we can simply find the I just multiplying the gs with the length. So from here we can integrate from where 0 to h to find the I enclosed within this particular of loop. So now 0 to h. So if you proceed to solve the equation, we can find here you have s hash x minus fh h equal to js h. So let's simplify. Can I have here 2hx s is equal to js hash. So now we can simplify the equation, becoming the hash in x component become 1 over 2 js. So let's find the hash that actually appear within this region. So let's say we have a js here given as 50, right? So you can put the 50 value. So 50 over 2 gonna have 25 milliampere per meter. And we know that the hash that actually appear here totally in x direction. That's why we have here in x component. So the hash here, if you have to put in vector, you can simply put here the hash becoming 25 x component milliampere per meter. Okay, how do we check? We can simply check the results, okay, by applying this simple formula for the case of infinite surface charge. So you can find the H of any infinite surface current, surface current. So just apply this formula, 1 over 2 Js from here, right? So just cross with the unit normal vector. Alright, so this is our surface current density given, and this is a normal vector that pointing normal from surface current to the point of interest. So in this case, this is our normal vector. Okay, again I repeat, the an here actually refers to the unit vector normal that pointing from surface current, which is the source of H field, normal to the point of interest. So this is going to be your an. Alright, so this case the an here becomes your negative y, directions. So simply put here a negative y directions, and then the Js as normal given in 50 z directions. So if you perform cross product between the Js and An here, you'll see, you'll get the answer becoming 25 in x component milliampere per meter. So we have the same answer as shown or as obtained previously. Alright, so guys, I hope you can try yourself and make sure you are familiarized with the surface current density case. So I hope you can do it yourself, and thank you.